Hello, everyone. Thanks for joining our fault tolerance processing semantics with Apache Apex webinar today. My name is Ian Gomez, Audience Marketing Manager here at Endtoend. Joining us on the webinar is Thomas Wise, Architect and Co-founder at Endtoend, and Pramod Imaneni, Architect at Endtoend. Here are some logistics regarding the webinar. This webcast is being recorded. It will be available after the session has ended to watch again and share with your colleagues who are not able to attend our session today. Second, we love your questions. Please submit your questions throughout the session. You can submit your questions via the Questions tab in your console, and we'll be happy to answer them after the presentation is over. Lastly, feel free to click Attachments tab below to view more relevant information regarding Endtoend and our solution. Without further ado, I'll hand it over to Thomas.
Hello, good morning, everyone. Welcome to our webinar. Our topic today is fault tolerance and processing semantics in Apache Apex. And I would like to start with a little overview about Apex before we dive into fault tolerance. So some of the features of Apache Apex that also make it unique or distinct to other similar platforms that are out there, it's an in-memory stream processing platform. It has features for scalability, advanced partitioning schemes. Since it's processing unbounded data, it also has the concept of windowing to establish time boundaries for functions such as aggregation. It also has a good set of reliability features. It tracks the state of applications. It performs automatic recovery, and it has strong processing guarantees. From the beginning, there was a strong focus on operability, going to production, running applications in production, and this operability focus will show in many ways in Apache Apex, and the fault tolerance concepts are part of that. It also has optimizations that increase performance and can increase the throughput significantly. Compute locality, we call them, the way you can arrange compute functions in different containers in the distributed systems, optimization to collocate things in containers and in threads. It also supports dynamic updates, changes at runtime. This is for elasticity in partitioning, but also for dynamic plan changes and configuration changes. With that, let's have a look at a system-level overview. In the overall picture, Apex is Hadoop native, so it runs on any Hadoop cluster that has Yarn and HDFS. It is certified to work with all the major Hadoop distributions. The cluster can really be anywhere. It can be on cloud, it can be on-prem, it can be physical machines, virtual machines. As long as we have a Hadoop cluster, Apex will run on it. Apex Apache project consists of two parts. It's Apex Core, this is the stream processing engine. And on top of that, a library of operators that makes it easier to build an application. Those are the functional building blocks. The engine will host the application at runtime. The operators is what you use at development time to assemble an application. Streaming applications run on Apex and on Hadoop. They inherit all the underlying features of Hadoop, including security and multi-tenancy, and the concepts that are built into Apex for fast, high-performance, scalable in-memory streaming. On top of that, Endtoend provides value-added tools for visualization, for data visualization, for management, and also for application assembly. There's a management REST API hosted by a service that we call Gateway that allows you to also write custom tools for monitoring or for managing applications at runtime. Originally, Apex was developed at Endtoend since 2012. It became open source last year, mid last year, and we are expecting it to graduate to Apache top-level project soon. It was built as native Hadoop integration or native Hadoop application. We started development in 2012 when Hadoop Yarn was first released. It was actually still at alpha stage, and development of Endtoend was a full bet on Yarn. In a Yarn cluster, you have node managers and you have resource managers. Node managers scale out horizontally. You can add more machines and more node managers, and that's the scale out architecture of Hadoop. Hadoop allows you to perform massive workloads on commodity hardware by adding more machines and more resources. In the Yarn architecture, the node manager is responsible for monitoring the distributed processes, and there's a central component called the resource manager, which will keep track of all the different node managers, and it will also detect failures. And the resource manager itself fails our HA options to set up a redundancy that are supported by all the major distributions. The workloads that are running on Hadoop clusters can be different for different processing paradigms. For example, MapReduce was the first there in the original Hadoop 1.0. There was only MapReduce, and Yarn was actually an abstraction of the scheduling and process management layer in a separate component, so that additional processing paradigms become possible. So different applications can coexist, different applications of different users, and they're all isolated completely with their own resource policies and in a secure way. So here we see an example with MapReduce and Apex application coexisting on the cluster. The Apex application has an application master. That's the term for the main process of every job that is launched on a Yarn cluster, and then additional containers that are launched by that application master. Here you can see with the numbers identified different operators that are deployed in containers, and the dotted green arrows indicating data flow. The data flow is implemented in Apex. It's in-memory streaming, and Apex implements also the data flow between distributed processes. There's no file system I/O involved. It is just memory and network I/O. To interact with applications that run on the cluster, Apex provides the command line interface, Apex CLI. And then, as I mentioned in the previous slide, DataTorrent provides additional tools to perform the same functionality with a user interface. There's the DataTorrent console. We also call it DT Manage, and DT Gateway, the management process that exposes the REST API that can be used by other tools to connect and perform the same operations. So there are two pieces that we are using of Hadoop: Yarn for acquiring the resources and for managing the processes, and HDFS for checkpointing. This is important for the fault tolerance that we will discuss now. We are using HDFS to store a state of the application that can be used for recovery, but not for the data flow and for the streaming itself. An important concept in processing unbounded data are windows. Apex has the concept of streaming windows. Streaming windows divide the data stream into small time slices. The way it works is actually that control tuples are inserted into the data flow. They travel along with the actual data tuples through the system. These markers are inserted periodically based on the processing time. All operators in the distributed system receive the same time markers. This enables us to take a consistent snapshot of state in a decentralized and distributed manner and use that state for recovery. As you can see here, the gray circles are the data tuples. They are a little bit hard to see in the slide perhaps, but the colorful circles are the control tuples that are inserted into the flow. So it's a stream of data, and every event is processed as soon as it arrives. There's no waiting for a micro batch to complete before we can start processing. The processor is handed each individual event for processing, which means that there is no artificial latency added. On top of the streaming windows, we have the concept of application window, which can be a sliding window or a tumbling window. These windows are exposed to the user. That means they are callback on the operators that are executed at the boundary of the windows, begin window and end window. and the user code can perform functions such as aggregation at these events, at these opportunities. The application windows are specified in multiple of streaming windows, and the default for a streaming window is 500 milliseconds. Again, 500 milliseconds is not an implied latency. 500 milliseconds is just the distance between two of these control tuples. The typical latency that you see with Apex applications is in very low millisecond values. Let's talk more about fault tolerance now. The operator state is checkpointed to persistent store. That means you have a compute unit that has some data in it, let's say a count, and we want to make sure that we don't lose the count even when a process fails. This mechanism is checkpointing, and it is automatically performed by the engine. There's no extra coding needed by the application or the operator developer. The checkpointing happens asynchronous and in a distributed manner. And in the case of failure, operators can be restarted from the checkpointed state. Failures of processes are detected automatically, and the recovery of failed containers is orchestrated by the application master. As part of that, it will identify all the affected pieces of the processing graph, and it will recover only those that need to be recovered. That means Apex supports incremental recovery as opposed to resetting the full topology. There's a heartbeat mechanism that is used to check the health status of the containers, and there's also Yarn's process status notification that will be used to detect process failures. We have buffering to enable replay of data from a recovery point. Buffering enables fast incremental recovery. It also cares for spike handling, intermittent spikes. That means the results are emitted to a buffer, and regardless of the speed of the downstream processor, the upstream processor can continue processing events. The application master state is also checkpointed. The application master is the brain of every Yarn application. It is responsible to maintain its state, and when Yarn restarts an application master, it needs to be able to recover and remember everything that is needed for its operation. So this functionality is part of Apex. Let's consider how checkpointing the operator state works in more detail. During checkpointing, we save the state of an operator so that it can be recovered on failure. To facilitate this, we have pluggable storage handler. It is an interface defined in the Apex API, and the default implementation of that interface is using Creo serialization library to save the state of the object, and then once it is saved, it will be written to HDFS. So the default implementation is Creo plus HDFS to persist the state of an operator. Now it is, of course, possible to implement custom storage handlers to do other things. For example, to optimize the extraction of the state. Let's say you wanted to save only 2 fields of and not the entire operator. You don't want to serialize everything. You can write such a storage handler. You can also use a different backend to persist the data, such an in-memory data grid. Recently, an implementation was added to our Malheur operator library to support this for Apache Geode. For operators that rely on the previous state for their computation, the state needs to be checkpointed. But for operators where that is not the case, checkpointing can be skipped completely, and the overhead of saving state, serializing and saving state to HDFS can be eliminated, such as an operator that performs a simple function that requires only the context of the event for its operation. Checkpointing frequency is tunable. The unit for that is the number of streaming windows, and the default is 60 with a streaming window with a 500 milliseconds that amounts to 30 seconds between checkpoints. The buffer server plays an important role for streaming the data between 2 processes, but also for the recovery. It's an in-memory pub-sub mechanism. Publishers send data to the buffer server and subscribers receive it. The publisher is the operator that produces data, that emits data tuples, and the subscriber is the operator that receives the data tuples and does some processing and then maybe emits it again to another buffer server. The buffer server is collocated with the operator producing the data within the process, and it doesn't need to checkpoint state. The buffer server's purpose is to maintain the buffer in memory and make it available for the downstream operator to subscribe and read the data. When there's a failure on operator 2, in this case, for example, operator 2 will be restored to a checkpointed state and it will subscribe to the buffer server from the point that is identified by the checkpoint window. That means it can go back and retrieve data tuples that it had retrieved before for replay and for recovery. The buffers are maintained until the streaming windows are no longer required. They are no longer required when they have been fully processed in the entire application and can be purged then. The buffer server is important to store the data for the stream. It also handles back pressure, and when it exhausts its configured capacity of memory, it will start to spill over to the local disk. That means an operator that is producing faster than the downstream operator can consume will be able to run at the speed of spilling to disk until the intermittent spike is processed and the streaming returns back to in-memory only. The buffer server maintains ordering of the windows, and this is important for the ability to replay events in an idempotent manner. What are we doing for the application master state? The application master orchestrates the application. It knows the logical plan. The logical plan defines which computations we perform and how they are arranged in sequence or in parallel. This state needs to be maintained because, as I mentioned earlier, it is possible to dynamically change the plan in Apex due to dynamic partitioning or due to changes performed by the user. Hence, we are taking a snapshot of the plan whenever it changes, and we are saving it to HDFS. This is a comparatively expensive operation, hence we don't always save the entire plan when changes occur. For other changes, we have a write-ahead log, and that write-ahead log will maintain the operations that have been performed, and we are able to replay those operations. Examples of such operations are a container was allocated, we need to remember the container ID, or an operator state has changed, or the user has changed the property of an operator, and we need to remember that across restarts. Containers locate the application master through the address written into HDFS. This is important when the application master fails and restarts and the container needs to reassociate to the application master. So it is a smart RPC client that will, on failure, retrieve the new address and connect to the new address. This is important for work-preserving restart, which will be supported with future Hadoop versions. On recovery, Yarn restarts the application master. When the application master process comes up, it is the job of the application master to retrieve the state. This is done by reading the snapshot back and then replaying the write-ahead log to apply all the changes on top of it. Let's go through some failure scenarios. One scenario is a container process fails. This could happen because somebody kills it or for any other reason. So if a container process fails, it is detected by the node managers. Think of the node manager as Yarn's agent that runs on every machine, and its job is to launch the processes, but also to monitor processes. Monitoring actually includes monitoring the resource constraints for applications. For example, Yarn will determine whether a process runs over its configured memory limit, and if so, it may kill the process, which is actually could be one cause for container failure. When a process gets killed or process fails and terminates, Yarn will notify the application about this event. The application can use it to take any action appropriate. In the case of Apex, we find out what operators the process has hosted, what other operators downstream are affected, and we will ask for a new container and recover the operators by going back to the checkpointed state and replaying any events. We will look into that closer later. It could also happen that in Yarn itself, a node manager process fails. This is something that is detected by the resource manager, and the resource manager will then notify the application master of any affected containers that were running on that node manager's host. When the machine fails, the resource manager will detect a node manager timeout or failure, and it will inform the Apex application master, or if the application master itself was running on that machine, it will relaunch the application master. When the resource manager fails, there's the resource manager HA option. The cluster was configured for HA. In that case, it will fail over to the standby instance of the resource manager. If the entire Yarn cluster is down, we still have some help to offer because we support stateful restart of an Apex application. That means if the cluster was taken down for any reason, could be for maintenance too. If it comes back up, you have the option actually to relaunch the Apex application from its previous state, and it will resume processing. Let's go through some couple of failure scenarios. So the first example that I want to bring here is what happens when an application master gets killed. So first, the application master process goes away. After the application master goes away, and this is the behavior as of Hadoop Yarn 2.2, the processes will be automatically terminated. Now, it is important, the other processes, the other containers, it is important to note that in the future Hadoop version, it is supported to keep the containers up and running. So now, after that failure was detected, the resource manager will relaunch the Apex application master. The Apex application master then remembers what it was doing, what resources it required, what its plan was, execution plan, and it will recover the execution layer. It will go and ask for new containers. These new containers, they will be typically now on different machines depending on what the scheduler assigns, and the application will be restored. All the operators will be restored from their checkpointed state, and the data will be replayed back to current. The other scenario that I would like to discuss here is what happens when an operator fails in detail. So let's say it was not the application master container, but it was one of the containers where this operator was deployed. So we have an example of a summation operator and a small stream of data. So we have a begin window, we have two windows and a few numbers that we want to add up in our operation. So we start from the initial state, which is 0. After the first window is processed, we have 1, 2, and 4. And so the sum will be 7. So this state is checkpointed. Let's assume this is a checkpoint window. So we have checkpointed the state of 7 for the sum after the first window was processed. Now we assume that there is a failure. After the second window started processing and the first number was added, the container dies and the operator is gone. So the recovery will mean now we are going back to the checkpointed state, which was 7. We restore that, and we rewind in the stream when this operator comes back to the checkpointed state, and the window is tagged with window 1. It will go back and resume after window 1 in the stream. So we rewind logically the stream to the begin window 2, and we replay the data. So this is how recovery in a very simplified way works in Apex. And now I will hand over to Pramod, who will discuss the processing guarantees.
Hello, everyone. So the processing guarantees determine what happens when you recover from failure. So our default mode is at least once. So in this mode, what happens is when there is an operator failure, the operator restarts at an earlier checkpoint and data is replayed from exactly that checkpoint. So essentially, no data is lost in this process. And this is our default behavior, and it's suitable for most applications. And this mode can also be used to ensure end-to-end exactly once, which I'll go into detail in the next slides. We also support at most once, which is basically if you don't if you don't care about data loss, and you essentially don't want to reprocess old data when you restart, you just want to start processing the latest data, and you can accept data loss, then this mode is for you. In this case, the operator restarts from the checkpoint and it starts processing the latest data. And exactly once, so exactly once is actually not just a platform feature. It's something that is done with the collaboration between operator and the platform, and it requires at least once. It requires idempotency and other transactional mechanisms that are specific to the external system the operators are interacting with to achieve exactly once. And we'll go into those scenarios in the next slide. Okay, so so when is end-to-end exactly once important, right? So it becomes important when you're writing to external systems. So what does it mean? What it means is that the data should not be duplicated or lost in the external system, even in the case of operator failures or application failures, right? So, and the common systems, common external systems, which streaming applications or even batch applications deal with, is writing to databases or files or message queues. To do this, the platform support for at least once is a must, which our platform provides. And then the operator on top will still have to avoid writing replay data again into the external store. So the operator would implement some custom logic that is dependent on the external system it's interacting with, so that data is written only once. And in doing that, it will still use platform features such as checkpointing and windowing, and we'll go into those in the next slides. And what we'll discuss here is three different mechanisms. 3 different strategies on how to do exactly once, end-to-end exactly once, basically 3 different use cases. Okay, so the first is when you're writing to files. So like let's say you're writing to a HDFS file or an NFS file. So what's happening here is data is streaming in and it is being written to a file on a continuous basis. Now, the failure can happen at any point of time, any random point of time, and in which case, now your file has an unknown amount of data, because there's buffering involved in between. Data is not immediately written to disk, and so on, right? So what our file output operator does is basically it works with the platform to ensure exactly once behavior. So the responsibility is divided into 2. The platform's responsibility is it will restore the state of the operator to a checkpoint and restart it to that checkpoint. And then it will replay the data from that checkpoint, right? And the operator's responsibility is not to write not to duplicate the replayed data in the file. And it does this, it accomplishes this by keeping track of the offset. This operator is actually implemented in a class called abstract file output operator, and it is in our Malhar library on Malhar project on GitHub, and the links are there if you want to go look at the code. And we also have a sample application, Atomic File Output app, that basically shows you how to use it in an application. So let's see what happens during a failure scenario with this file output operator. So first, so your data is being written to a file, and in a progressive fashion. So in the slide here, you're basically seeing the file data. I'll just give a few seconds for the slide to load. I know it's some people are seeing a little bit of lag. Okay, so so here it's basically showing the output file as the data is being written, and periodically the operator state is being checkpointed as well. So the arrows show the point of time when the operator state is checkpointed. The data in the file the file doesn't contain any markers or anything like that. It's just a standard file. And the checkpoint state is being saved elsewhere, like Thomas described earlier in HDFS. So these checkpoints are happening, and then let's see what happens during a checkpoint. So during a checkpoint, what happens is the current offset of the file is saved as part of the state in the checkpoint. So if the operator fails, it will be restored, and this offset would be restored and available to the operator, right? So let's say there's more data returned to the file, there is a failure, and once when this failure happens, then the app master recognizes that the operator has failed, and it will recover the operator to the checkpoint. And what the operator will do is, since the platform will restore the state, the operator will have the offset of the checkpoint. So it will truncate the file back to the checkpoint, the offset at the checkpoint, so that its state is now consistent with the data in the file. And when the data is replayed, it starts writing the data back to the file. So this way, you don't lose any data, and there are no duplicates either. Okay, and on the right, you'll see the steps that I just described, listed in detail. Okay, so there's a question from the audience. Do the windows need to be uniform, or can some be smaller than others based on criticality need? Yes, each operator can have windows of different sizes based on its application needs. So the application window can be different for different operators. So next, we'll see a scenario where you are writing to transactional databases. How would you achieve exactly once? So in this case, our operator that we have makes use of streaming windows. It will use the transactional features of the database. It will store the window ID that is being that is committed. I mean that's fully processed into the database, and it will use that for recovery. So this particular operator is implemented in the abstract JDBC transactional output operator class in the Malhar library, and we have a link for an example application that uses it as well. And then let's go into detail on how the exactly once works in this scenario. So as the data is streaming in, as the windows are streaming in, the operator is writing data to a database table. The table, the columns, all these are configurable, but it's actually what it's doing is it is writing the data that belongs to a window in a single transaction. So it can be guaranteed that the writes will be committed atomically, or if the commit is not called at the end of the window, the partial data would be discarded. Now, along with the data, the last processed window ID is also written to a meta table as part of the same transaction. So here in this picture, you see that the last processed window ID is WN. So the meta table has a single row where we are writing WN and we are storing that information. Now, if there's a failure, what's going to happen is the operator would be rewinded to the checkpoint, and it'll start receiving windows from the checkpoint window, from the checkpoint window, which could be less than WN. But what the operator does on restart is it reads this meta table and gets the last process window ID, and it will ignore all the data for windows that are less than or equal to this window ID. So it will not write them again. And only when it starts receiving data that is greater than the window ID WN will it start writing that data to the database. And that way, it's going to ensure that there's going to be no data loss. And because we are writing the entire data in a window in a transaction, the window that was being processed when the operator had a failure, that data would be discarded because that transaction was never committed. Okay. Again, I have enlisted these steps on the side. So the next one is writing to a stateful message queue, such as Kafka. So you have data that's being written out to a message queue like Kafka, where which keeps track of the offsets. And here we need to ensure that on failure, that the data that's already sent to a Kafka queue is not going to be resent again, right? Because there are consumers that are reading from the queue. So here, the way we achieve exactly once is that we would send a key along with the data that's monotonically increasing. And on a recovery, the operator would ask Kafka on that topic and partition to give the last message, and it will retrieve the last message. And from the last message, it will retrieve the key. And what it will do is the data that's replayed from the checkpoint, it will ignore all the data where the key is less than or equal to the recovered key. And it'll only start writing data when the key that's coming in is greater than the recovered key. Now, if the key that you have is not monotonically increasing, then you can modify this operator slightly, where you collect the data that's coming in during the window, and at the end of the window, you sort it and then send to the message queue. This operator is available as well in our library. It's called the abstract exactly once Kafka output operator. Okay. So these are the three different strategies I wanted to show you on how you could do exactly once, end-to-end exactly once in your operator. There are other possibilities, other ways of doing this as well, but they all require that the engine underneath to support stateful recovery and some sort of windowing. And you can find more examples in the Malha library. If you're interested, we have some resources, links to some resources here. You can go to the Apex community page. There are a couple of mailing lists. Based on the interest, you can join the users list or the dev list. You can also download Apex and give it a try. You can also follow us on Twitter and Facebook, and do look out for the meetup page on upcoming meetups. And that ends the presentation. We'll take any questions you have now.
Great, thanks, Pramod. We have a few questions in the chat window, and we will answer them as time permits.
Okay.
So one question is, which operators cover exactly what?
So our library contains a few operators. Pramod has given some examples of operators that support exactly one strategies. Many of our operators actually support this. It depends on the capabilities of the exact external system. So Pramod gave a good overview of several mechanisms, how it works with files, how it works with a message queue, how it works with a transactional database. So those are three important categories. They can be mapped to several other external systems. For example, any transactional store would solve the same pattern that Pramod described, where you use the transaction to ensure exactly once. Message queues have different capabilities. Some, for example, support the notion of the last message queue, where you can find out what was already published and don't publish it again, and as such. So it really depends, but we try to implement these things for the operators that we have, because we realize that this is really what the user needs, and it is not easy to find that out on the application level, which is a question that is left open by many other similar platforms, actually.
Awesome. Thanks, Thomas. We have another question. Do you support exactly once writing to other message queues?
So yes, it could be done. For example, we can take an example of Solix, for example, which has a last message queue, the last message value concept. In that case, we would implement, instead of Kafka, where it's based on the key, we would determine what was the last message written, and we would not write it again. This, of course, would require provision in the operator so that the ordering of messages is consistent between reruns, so that on replay we present the messages in the same order, and we can find out till which point it was already published. So there are a few more questions here from the audience in the message tab. Maybe Pramod, you can take the next one.
Are there any examples of exactly one strategy when calling external systems web services for data updates? So here we would actually require the external system. We would need to be able to have a way to ask the external system what is the last piece of data that was published. In that case, we can on the recovery we will basically not send those again. But that would be a facility we would need from the web service. Otherwise, you cannot do exactly once, but you can get pretty close, because we can still save the window ID in the state. So we basically will not replay fully finished windows, but you would end up replaying the partial window if you don't have that. Yeah.
Okay, so I think we covered the questions, and the time is almost up. Before I hand it back to Ian, just a quick note: we are going to add a few more links and resources to this webcast after it's over, pointing you to some of the code examples and useful reads that cover the processing semantics and the fault tolerance. Also, we will attach a few other resources that have to do with introduction, how Apex applications are specified, and so on, because this was focused here on fault tolerance. Ian?
Great. Thanks, everyone, for joining our webinar today. That ends our webcast. Look out for more webinars hosted by us in the next few weeks. Have a great day.
Thanks, everyone.